Great. Okay, so today our mathematician spotlight is Erik Demaine by request. So Douglas requested Erik Demaine. You're welcome to request anyone that you'd like. So Erik Demaine is a professor of electrical engineering and computer science at MIT. And he works on origami and computational geometry. So he was actually a child prodigy. He grew up in Canada, and he was homeschooled. So he and his dad drove around Canada and the United States and did stuff. I read an interview with him where they asked him, why did you do homeschooling? Why didn't you go to school? And he said, well, with the 6 hours of the school day, only about 2 hours of that is actual instruction. So it seemed like kind of a waste of time. So we decided to do other things. Seems kind of neat. So he, in his PhD thesis, he proved something called the fold-in-one-cut theorem. So this is something that had been known by people for a while. Like, for instance, in the 16 or 1700s in Japan, there was a math book for clever children, something like that, and it had these shapes. And the idea was you were supposed to figure out how to fold up a piece of paper so that when you made one single cut, it would exactly cut out the shape. It's pretty cool. So in his thesis, Erik proved that no matter what shape you draw on your piece of paper, as long as it's a polygon, but every shape can be arbitrarily approximated arbitrarily closely by polygons. So whatever polygon you want, maybe it's a star or a turtle or a tower or an airplane or whatever you want, there's some way to fold up the paper so that you can make a single cut and cut it out. And the argument is constructive, so he says exactly how to do it. Pretty cool, right? So I'm going to show you a magic trick. So you should have a piece of scrap paper. If you don't, you should pick one up. There's a pile at the beginning. Good? Okay, so here it is. This is a trick that Houdini, the mathematician Harry Houdini, used to do. So as you can see, this is a perfectly normal piece of paper. Nothing magic about it. I'm going to fold this up and with a single cut out a perfect 5-pointed star. It's got to be magic. Okay, so here's how you do it. So take the paper and fold it the short way so that you get the shorter kind of rectangle. Good, and make a little crease, make a fold. Good, everybody there? Yes? Okay. Now what you want to do is you want to find the center. So fold it in half, but don't make a crease. Just find the center. I found the center. Yeah? Did you find it? Fold it just a little till you find it. You don't have the center yet. Fold it again. So I folded it again. Fold it again. I know my paper is so much bigger than yours. Now find the center. Good, you've got the center. Okay, now you want to sort of make it like a flower. So we want to have like 5 equal petals. So what you want to do is pull this part over until this sector is half as big as this one. So the angle over here is half as much as the angle over here. So that's approximately right. I don't know. It's approximately right. So something like that. Yeah? You got it? Okay. Now we want to fold it over so that all the 5 pieces are on top of each other. So take the far end here, the big fold, and fold it over onto the sector like that. And now you can see if you got it right because you can see if these 2 sides are equal, which is what you wanted. And now with this little side, we want to fold it down. So you could fold it to the front, but it's probably better if you fold it to the back. There's more space there. Okay, so now we have sort of this triangle where this is like 1/10 of a circle. You got it? You stopped. I got lost?
After the petal.
After the petal? Okay, so you find the center and then push this over until this side is twice as big as this side by angle. Yeah, and then fold it down. Good. Now we want this side to be like fold this down so that the 2 sides are equal. So fold this fold over to this fold. It looks like a paper airplane. Yeah, similar to making a paper airplane. Yeah? And then finally the last little fold it to the back. And if you estimated correctly, they should all be triangles on top of each other. If you didn't, it's okay. No problem. Now, the last thing is to make the cut. So we're going to make this into a triangle. If I cut this like a isosceles triangle, I would get a decagon. But I don't want that. If I cut it perpendicular to one of the edges, I would get a pentagon. But I don't want that. So I'm going to cut it at quite a severe angle here. So, like that. So I have scissors. I didn't have enough for all of you, so I didn't bring them for any of you, but you can borrow mine. So I'm going to make it quite a severe cut here. Ready? Bink! Ta-da! Okay, here. Can you open this piece? Can you open this piece? What did you get? What did you get? Hold it up. Wow! Yay! Magic! Did anybody else get it? Are you able to tear it with your fingers? Or use scissors? Scissors? That is so cool. Pass them around. So cool, right? So if you didn't get it the first time, there's more scrap paper. You can try again. But it's such a cool trick, right? You can impress your friends, Skype your parents. Yeah. Yeah, nice. So good. So good. Anyone else get one? Yay! Nice job. Yeah. So cool. You got one too. Great. So maybe take another piece of scrap paper and practice so you remember how to do it, and then impress your friends and everyone else, really, in your life. You can keep it. Yes. Good. Good.
You're my missing star.
I get it.
So nice. So many stars. And a pentagon. Yeah. Good. So nice. Such good stars you all have. So if you want to throw away your paper, I brought this bin for recycling. You can practice again. What did you get? You got a butterfly.
It's a butterfly.
Yeah, nice. Okay. Okay. Great. So, good trick. Practice. So you will remember. Good. Okay. The moment of truth. Did you get one? Oh, go. Good job. Good. We could have maybe a little gallery of stars. So nice. Okay. Did you get one? No, you are sad. Oh yes. So what happened was when you folded to the center, you used the center not on the fold side but on the flap side. So when you folded it in half, and then you found the center, you didn't find the center on this side, you found the center on this side, and folded from this side. Okay, but it's okay. You can try again. There's more scrap paper. Okay. So one of the themes in this class, maybe the major theme, is that we take an idea from single variable calculus and we generalize it to multivariable calculus. So that's how it's going. So we've done that with functions of multiple variables, or functions that map to multiple variables instead of just to a single variable, and also with the derivative. So in single variable calculus, derivative is the slope. That's it. But in multivariable calculus, there are multiple ways to go. So you have to have the directional derivative, which says, if I go in this direction, what will my slope be? So the next thing, maybe to generalize, is the integral. So that's what we'll do today. So today we start with integrals. So in single variable calculus, as usual, you have the x-axis, the y-axis, and you have some function. Here it is. So there's f of x. And your burning question is, what is the area under my function? Maybe this f of x represents a particle that's moving with a certain speed, and this is the velocity. And so if you integrate, you'll find the position. Where's my particle? I want to know. So you'd pick like some value here where you want to start, and some value here where you want to finish. And then you'd want to know the area. So we want to know this area. So if we call the interval from a to b, if we call that interval I, then the area, this area here, is just the integral over the interval of f of x dx. And what f of x dx means is you pick an x in this interval, like maybe this one, it's my favorite x, And you compute f of x at that interval. Maybe I should get a color. So you pick your favorite x, and you compute f of x there. F of x is the height. And then you multiply by a tiny thickness, dx, and that's the area of this little box. And then you add up the area of all these little boxes for your whole interval, and it gives you the total area of the thing. As a reminder, I've drawn this dipping below the x-axis, and when you have area below the x-axis, you usually take it as negative. An area above is taken as positive. So this area, you could think of it as like a net area, as positive area minus negative area. Yeah. So with multivariable calculus, we have surfaces. So instead of finding the area under the curve, we'll find the volume under a surface. So here's some surface. I'll just draw one. So here's f of x comma y. That's our z value. And it's sitting over some region in the plane. OK? So this is the xy plane here. Maybe this is the x-axis, and this is the y-axis. So this region here, let's call it R. That's the region over which you care about the surface. So I might want to know, what is the volume over my favorite region, R, and under this surface? So pretty much like the volume that I've drawn here, this box with a curvy top. And the volume, so the volume is the double integral over the region of f of xy. OK, so at any point here, my favorite point, x comma y, I compute the value of the function. Maybe it's this. So this distance is f of x comma y. And then to make it an area, to make it a volume, I have to multiply my height by the area of a little box. So I'm going to turn this into like a rectangular box. So I multiply the height, f of xy, times the tiny area of my box. So this is f of xy dA. So instead of a little dx length, it's a little dA area. And that gives me the volume. Yeah?
Why a double integral?
A double integral because we're integrating over a two-dimensional region instead of a one-dimensional region. So right here, it's sort of abstract to have two integrals. But as soon as we write one down, you'll see we have to integrate with respect to x and with respect to y. So similar to partial derivatives, exactly. Yeah. So that's the thing. We want to do this. Oh, and similarly to over here, where the function can dip below the x-axis, if this function dips below the xy plane, then we take that to be a negative volume. I thought it was beyond my artistic ability for right now to draw something, but you can imagine if you dropped a bowling ball on this, it would dip below and give you a negative volume for the part below. And that would be the negative part. Yeah. OK. So let's write down some integrals and try to compute them. So how about if our region is x, we want to compute the double integral where x goes from 0 to 1 and y goes from 0 to 3 of the function 2 dA. That's our dream. What does it, first we'll figure out what it means, and then we'll try to compute it. So when I have this notation, it always means x is always first, y is always second. It means y is in the interval, x is in the interval 0 to 1, and y is in the interval 0 to 3. So x is going from 0 to 1, and y is going from 0 to 3. So our region is this 1 by 3 rectangle. There it is, R. And our function is f of xy equals 2. So let's draw the z-axis. Z is going up to 2. So the function is just a flat z equals 2 plane up here. OK. So here, up here, is our plane z equals f of xy is 2. and we want to integrate this. So can you see what this integral should come out to? What should it come out to? Yeah, 1 times 3 times 2, or 6. Yeah, it's just the volume of this box. 1 times 3 times 2. So 6. Yeah. Nice. Okay, great. Okay, so let's try one that is slightly more complicated. So let's compute the double integral over the region where x is from 0 to 1 and y is from 0 to 2 of the function x dA. Okay, so the first thing to do always in all problems, I think, is to sketch what's going on. So the first thing, let's see, is to draw the x-axis, the y-axis, and the z-axis. By the way, when we draw these axes, we have a choice about how to draw them, but you have to draw them so that they follow the right-hand rule. So one way to draw them is like x and y in the usual way, and then have the z-axis coming out toward you. You just imagine that the z-axis is coming out of the board. That follows the right-hand rule because if you take your right hand, you put your fingers in the direction of x, and you curl them toward y, then z points out toward us, which is what we want. Similarly, over here, if you put your fingers in the x direction, we kind of imagine that x is coming out toward us in this picture. Curl them in the y direction, z points up. Another option would be to put x here and put y back into the chalkboard. That would be like taking this picture and just rotating it a little bit. You wouldn't, however, want to put y here and x back there, because then it would not follow the right-hand rule. Yeah?
Is there like any geometric intuition behind that, or is it just for consistency across like mathematicians?
It's for consistency. We've decided that axes should always follow the right-hand rule. Sometimes if you switch and go with the left-hand rule, sometimes things will come out negative that should come out positive. So it's a convention, just like driving on one side of the road versus the other. It's not that one of them is better, it's just a convention that we decide to all do so that we can talk to each other. Yeah. Okay, so let's see. X is supposed to be from 0 to 1. That's here, 1. Y is supposed to be from 0 to 2. So here's our region. And now we want the function x. So that's like f of xy equals x or z equals x. So let's see, we'll have to draw one more picture. Here's the zx plane over here on the left side. So if z equals x, I'll just draw it like this. Z equals x is like the line y equals x, just looks like that. But here, in this view, the x-axis, positive x-axis goes over to the left. So you might actually want to flip this backwards. Draw that positive x-axis going that way, the positive z-axis going that way, and then the line z equals x looks like this. So I just took this picture and went, whoosh, flipped it over, because that's kind of how it is here. So z equals x looks like this. Here's z equals x. And it's not just a line. Z equals x doesn't have y in it. Y can be anything, so it's a whole plane. So it's this whole plane at a slant, kind of like that. So we want to know what's the volume over our region R and under this slanted plane. So we want to cut it off however far out we go. So we go up to here. So I'm going to erase the rest of this because it's a little bit confusing to have it there. Okay? And then we get this little shape. So it looks kind of like a shed. Nice hat. Okay. Okay, so it looks kind of like a shed with these triangle things. So let's try to find the volume of this thing. We were just trying to find the volume of our shed. So one way to do it is, my favorite way perhaps, would be to say, if it's half of a box. If you had made the whole box, we could find its area, then let's take its volume, let's take half of it. So the box is 1 in the x direction, because x goes from 0 to 1. 2 in the y direction, because y goes from 0 to 2. And then 1 in the z direction, because z is equal to x, and x is going from 0 to 1, so z is also going from 0 to 1. So if we had the whole box here, so it's half the volume of the whole box. If it were the whole box, So it's half of 1 times 2, so it's 1. So the volume of our shed is 1. Another way to think about it is that it's a triangular prism. So the side is a triangle, and then we multiply by the height. So it's the volume of a triangular prism, which is the area of the triangle times the length. So that's 1/2 base times height times the length. So 1/2 times the base of the triangle is 1, the height of the triangle is 1, and then the length of the prism is 2. So again, the volume is 1. Okay. Okay, so if you're just trying to find the volume under some plane over some rectangle, you could use basic geometry to make it happen. But you might imagine, like in this curvy surface that I drew at the beginning, you can't do it with basic geometry. You're going to have to use calculus. So we can do this algebraically. So before we do that, though, questions or ideas? Okay, so the way that we would do this is that so compute let's compute the integral algebraically by using calculus. Okay, so we would write down that we're trying to integrate the function x, and we're going from x equals 0 to x equals 1. That's here, x equals 0 to x equals 1 dx. And we're going from y equals 0 to y equals 2. That's here, y equals 0 to y equals 2 dy. So on our limits of integration here, we've just written down the limits of our rectangle here, what this means. Okay, now this might be a little bit scary because it's a double integral. What does it possibly mean? But all it is an iterated single integral. So you know how if you have a horse, horses are afraid of bridges? So if you want to take your horse over a bridge, you put blinders on the horse. Because if the blinders are on the horse can only see the road, and it thinks it's just walking on a road, and it doesn't know anything about the water. So this is what I'd like you to do. Put on blinders, so all you see is a single integral. You don't have to worry about the integrals outside. Yeah, exactly, just like that. That's good. So as blinders, I'm going to put this like parentheses around it. So here are our blinders, and we're only going to look on the inside. We're going to do this part first, and then worry about what is outside. Yeah?
Can we have switched the order and integrated with respect to y first?
Yes, we could have switched the order and integrated with respect to y first, and in fact, that's what we'll do after. Never fear, we will do them all. Okay, so let's do this inside first. I'll just copy the outside, y equals 0 to y equals 2 of whatever's inside dy. Okay, let's compute what's inside. Integral of x with respect to x. X, what? X squared divided by 2, right? Okay, x squared divided by 2, and we're going from x equals 0 to x equals 1. So this is just exactly what you did in single variable calculus. Okay, so I'll just copy the outside, y equals 0 to y equals 2 times whatever is inside, dy. Okay, so when we compute x equals 2, we plug in x equals 1, x squared over 2, plug in x equals 1, we get 1/2. And then when we plug in x equals 0, we get 1/2 minus 0. So this is just 1/2. Okay. Now, you can take off your blinders because it's just a regular single variable problem again. Good. So can you do integral of 1/2 with respect to y? 1/2 y. And we're going from y equals 0 to y equals 2. So this is 1/2 times 2 minus 1/2 times 0. So it's 1. Which is what we got before. So it worked out. That's good. Okay. So then, the natural question to ask is what happens if we do it in the other order? Let's try it in the other order. So we'll write it out again. So now we're going, the integral on the outside is from x equals 0 to x equals 1. The integral on the inside is y equals 0 to y equals 2, x, but now dy dx. So again, put on the blinders so that you don't worry about what is outside. Copy the thing. Copy the outside, whatever it is, integral from x equals 0 to x equals 1, eventually dx. OK, let's deal with what's inside. What is the integral of x with respect to y? Yeah, xy. So this is something we haven't talked about, except that we talked about it in partial derivatives, that with respect to y, x is a constant. So in the same way here, when you're doing things with respect to y, anything with respect to x is just a constant. So it's just x times y. OK, so x times y. And we evaluate from y equals 0 to y equals 2. OK, let's compute that. I'll just copy the outside integral, x equals 0 to x equals 1 of something dx. We'll figure out what to put inside. OK, we plug in y equals 2 here. We get 2x. And then subtract off what happens when we plug in y equals 0, which is 0. So 2x minus 0. So inside we get 2x. OK, great. And now we just have a single variable calculus problem. So integral of 2x with respect to x, x squared. We go from x equals 0 to x equals 1. We get 1 squared minus 0 squared, which is 1. Yay, so it comes out the same. Yes. So good, yeah, question?
Are there functions where the order with which you integrate with respect to like matters? Like if you try to do it commutatively like that, it wouldn't work?
Yeah, so there are times when the order you integrate in matters. So we'll see an example today where there's one order of integration where it's just impossible. You can't compute it. It's not only hard, it's impossible. So in one order, you're stuck. So you really want to switch the order. And the other question would be, are you always allowed to switch the order? And the answer is basically yes. There are functions where when you switch the order, the value changes, but it's very hard to construct such a function. You never run into them in life. So we will not have to worry about it. In every situation that we'll consider, you can switch the order. And that's called Fubini Theorem. And we'll talk about that at the end. Yeah, other questions or ideas? Well, maybe a burning question to ask would be, what on earth does this double integral thing even mean? I mean, I wrote it down, and you didn't complain that I was writing down x dx dy with these limits of integration. So let's see what it actually means. So we're going to draw pictures for what these things actually mean. And here's what they mean. As you remember, when you do a single variable integral, you're finding an area. So what this thing is, inside the first integral, is an area. We find an area. Then we thicken it up a little bit. So it's like, I think of it like a Jell-O mold. Have you ever had a Jell-O mold? It's like a bunch of Jell-O. And you could take it, and you can imagine slicing your Jell-O mold into very thin slices. So each of those slices is basically an area times a very tiny thickness. So we take our area of our Jell-O slice, and we multiply by a very thin thickness, and then we add up all those areas, and we get a volume. So that's the idea. And let's actually write it down and draw some pictures. So the question is, what do double integrals mean? And the answer is basically that the inner integral is the area of a slice. So you take the volume that you're trying to find, and you take a slice, and you find its area. And that's maybe a function of where your slice is. And then the outer integral adds up the area of the slice times a tiny thickness to get the total volume. So that's what it's doing. So let's do an example. So the first order of integration was x was on the inside. So we went from x equals 0 to x equals 1 of x dx dy, and y was going from y equals 0 to y equals 2. And our first thing that we did was the part inside. So I'm going to draw this picture again. So x was going from 0 to 1, y was going from 0 to 2. And we go up to z equals x. Okay, so the first thing we do is we take the integral of x, this integral with respect to x. Now with respect to x, y is a constant. So we're just basically holding y constant. So pick your favorite y value, maybe it's here, and draw a slice at this y value. So that looks like something like this. Okay, so there's the slice. So this integral is finding the area of a slice at like y equals a constant. So it's finding the area of this slice. When we computed it, let's see. We said it was x squared over 2. We computed that. We got 1/2. So when we computed this, we actually got that that's the integral from y equals 0 to y equals 2 of 1/2 dy. So we got that the area of each slice was 1/2. Does it make sense? Yeah, right? Because this little triangle, its base is 1 and its height is 1, so its area is 1/2. So indeed. And as you can see, that doesn't depend on y, because no matter which y you picked, the area was always the same. It was always 1/2. So then we took this 1/2, we thickened it up a little bit, dy. So we made it a little thick in the y direction, made it into a bit of jello. There it is. And then we added up all these volumes, and we got that this was 1. Okay. Pretty cool. Let's try the other direction. So in the other order of integration, we were doing the outer integral from x equals 0 to x equals 1, the inner integral from y equals 0 to y equals 2 times x dy dx. So the first thing we did was this inner integral. So I'm going to draw this picture again, one more time. So x-axis, y-axis, z-axis. X is going from 0 to 1. Y is going from 0 to 2. And then we're going up to x equals z. Okay, so the first thing we do is we're integrating with respect to y. So we're holding x constant. So to draw a picture, pick your favorite value of x. Maybe it's like here, 1/3. And draw a slice at x equals a constant. So I'll bring this down so I can write. This is the area of a slice at x equals constant. So if I slice in the x direction, I'll get a rectangle. Something like that. Can you see it? And allegedly, this computes the area of that slice. So let's see what we got. Copy the outer integral again. On the inside, we got 2x. So allegedly, at any x value, the area of this rectangle is 2x. Yeah? Makes sense? Yeah, because its length is 2, because y goes from 0 to 2 here. So this is 2. And then its height, well, its height is the z value, but z equals x. So its height is actually x. So it makes sense that the area of this rectangle is 2x. So this is the area of this rectangle. And you can see that in the first case, the area of the slice was always 1/2. It didn't depend on x at all. But here it does. Here, depending on what x is, the rectangle is different sizes. If it's far away, it would be small. If it's close to you, it would be big. And then we added this up, and we got that this. So then we thicken it in the y direction with a in the x direction. This is the x direction with a tiny little dx to make it into a little jello slice here, and then we add all of those up to get the total volume. So that's what it's doing. The inner integral is finding the area of each slice as a function of the outer variable, and then the outer integral adds all those areas up times a little thickness to get a volume. Yeah, question?
In high school calculus, we did problems like this where we would like geometrically find one of those slices and then iterate in terms of x or y.
Yes.
Are you doing stuff like that here or just doing double integrals? Because that's conceptually a little easier.
Yeah, so you can set it up as a single variable problem where you find the area of the slice and then you multiply by the d times the variable that you're in. And here we'll just do them as a double integral or triple integral because it's a new skill. So there are things that you could do that way, and you can also do them this way. But maybe there are things that we could do this way that we couldn't do that way. So we're giving you a new tool. Although you're welcome to use any technique that you know that works. Yeah?
So we were talking about surfaces in 3 dimensions.
Yeah.
If you go to upper dimensions, do you just keep adding integrals?
Yeah, so here we have a surface which is a function of 2 variables. And if you go up a dimension, you can keep adding variables. So for instance, you could have the triple integral over a 3-dimensional region, like a solid. Maybe it's like a ball. Maybe it's like your head. I don't know. Of some function of x, y, and z dv. So in single variable calculus, dx. And then in 2 variables, d area, dA, and now dv. So you could think of this as like maybe your solid has different densities at different points. And you want to know the total mass of the solid. Maybe this function gives your density at each point. And then this will give you the total mass of the object. Or maybe you have a chunk of like some kind of metal or something that's charged, but has different amounts of charge at each point. So maybe this gives you the amount of charge at each point, and then this will give you the total charge of the object, something like that. Cool, right? Yeah. So what we'll do is we'll do double integrals for a few days so that we get really good at double integrals, and then we will move on to triple integrals, actually. So that's the plan. Yeah, other questions? Okay, so I'll write down a theorem that says you can always switch the order, and then we'll do an example of when we would want to switch the order. So, Fubini's theorem says that if you're integrating a nice function over a rectangle, you can always switch the order of integration, just like we did here. No problem. So when integrating over a region R of the form A comma B cross C comma D, as long as your function f of xy is sufficiently nice, which r's will always be. So for example, if it's continuous everywhere over a region and differentiable everywhere, we're good. You can switch the order of integration. In other words, the double integral over the region of f of xy dA is the same whether you first go from x equals a to x equals b, and then from y equals c to y equals d, f of xy dx dy, or whether you first go from y equals c to y equals d, and then you go from x equals a to x equals b of f of xy dy dx. And all this means, of this form just means it's a rectangular region. So I'll draw it over here maybe. X is the interval a comma b. Maybe a is here and b is there. So there's our interval in the x direction. And then maybe c is here and d is here. So there's our interval in the y direction. It would just mean that we are integrating over this rectangle. This is a comma b cross c comma d. So it's just an axis parallel rectangle somewhere in the plane. Yeah?
Does this only apply to, I guess, the double integral, or does this apply to higher?
This theorem only applies to double integrals, but I believe the same is true in higher dimensions as well. Yeah. As long as things are nice, you can switch the order. Yeah.
It's similar to how the derivative of xy is the same as yx. So shouldn't that apply for?
Oh, is it like a generalization of Clairaut's theorem?
Yeah, that's right.
Right.
Is it related?
I'm not sure. I'm not sure if it's related. It sounds related. I'm not sure if it's related. I should check that. Good question. Yeah.
So in single variable, sometimes we were dealing with functions where they were discontinuous at a specific point. So what we did is we kind of split up the integral from like the end point up to that point, and then added the integral from that point to like the other point, the other end point.
Yeah.
And we do like similar operations with double integrals like that.
Yeah, so you sometimes you want to split the integral up, and yes, we can split the integral up into multiple pieces.
Okay.
And we will. Sometimes one piece you can compute it one way, a different piece you can compute it another way. Yeah, good question. Huh. Okay. Okay, so let's do an example of something where you would need to switch the order of integration. So, suppose you want to compute the integral from y equals -1 to y equals 1 of the integral from x equals 0 to x equals 1 of y times sine of x squared dx dy. Did I get that right? Good. Yep. Okay, great. Okay, so this would mean you're integrating over the region. Let's see. X is going from 0 to 1. Y is going from -1 to 1. So you're integrating over this box here. So there's your region R. And here's your surface is like y times sine x squared. So it looks like something. I'm not sure what it looks like. But when y is 0, this function would be 0. So here it would be down, like nailed to the axis. And when y is positive, I think it would be positive. When y is negative, I think it would be negative. So who knows what it looks like, but it looks like something over this. And you want to find this volume. You need it for some reason. Okay, let's do it. So the first thing to do is put on our blinders and integrate this thing. So with respect to x, y is a constant. So we just have to find the antiderivative of sine of x squared with respect to x. What is it? Yeah, you don't know it. It doesn't exist, actually. It's not possible. So this antiderivative of sine of x squared with respect to x, there is no antiderivative. You might be thinking, wait a second. I can anti-differentiate that. The antiderivative of sine is negative cosine. So negative cosine of x squared. If I take the derivative of this, I'll just multiply by 2x. So I have to adjust for that by multiplying by 1 over 2x. It's there. There. I found it. An antiderivative for that. There it is. But we could check if this is the antiderivative by taking the derivative and checking that it equals sine of x squared. And when you go to take the derivative, you'll have to do a product rule. So it's not the antiderivative. So this is a wonderful dream, but it is not the antiderivative for this guy. There is no antiderivative. Okay. There just isn't. Right, it's crazy. Yeah.
Well, what happened if you tried to use like a Taylor series?
Oh, if you tried to use a Taylor series. Oh, then I guess you could integrate term by term. Okay.
It would take forever.
okay, that's probably a good idea. Yeah, I guess you could do it with a Taylor series. Good. Fine. Then it would be a polynomial, which would be easy to integrate. Let's do it, but not right now. Turns out there's an easier way. But good idea. So maybe use Taylor series. Okay, cool. But there's one other trick that we can have in our pocket, which is to switch the order of integration. So let's switch the order of integration. So I'll do my x on the outside from x equals 0 to x equals 1, and I'll do my y on the inside from y equals -1 to y equals 1 of my function y, sine of x squared, and now it's dy dx. So let's first compute the inside. Okay, I'll rewrite the outside from x equals 0 to x equals 1 of whatever's inside, dx. Okay. So the integral of this thing with respect to y, well, with respect to y, sine of x squared is a constant. Yes, so much better. And then, so we just have to integrate y dy. So y squared over 2. Okay, so this is y squared over 2 times sine of x squared, and we're going to plug in from y equals -1. I'm running out of space. Okay, plug in from y equals -1 to y equals 1 dx. Okay, let's do it. So on the outside, x equals 0 to x equals 1 times whatever's inside dx. Okay, when we plug in y equals 1, 1 squared over 2 is 1/2. So we get 1/2 sine x squared minus whatever happens when we plug in -1, also 1/2 sine x squared. So 1/2 sine x squared minus 1/2 sine x squared dx. Okay, so 0. So we're integrating from 0 to 1, 0 dx. So it's just 0. Yay. All right. Well, thanks, everyone.